This week, we'll work on mirrors and lenses. So in this lab, the big idea is to learn about how the light beams get bended from mirrors and lenses, and how can we apply that idea into real life applications. So we will be using two simulators in this lab, and in this video, I will show you how to use these simulators properly. So let me share my screen with you to go over the simulators. So when you open in the first simulator, it should open a page like this one, exactly same as this one. And if you see any drawings, you may delete those. I'll show you how to delete the pieces. Anyway, so if you're seeing a screen like this one, that's great. So in the first case, we need to use select a beam. So if you are really in the real lab, we will be using a white light, and it's covered with a beam splitter where we can obtain parallel light rays. So here we can do this exactly same thing. So if you go to the tools and if you go to beam and select that one, and then move your cursor into the black area here, and then simply draw a straight line. I would keep it perpendicular as much as I can to the screen here, to the horizontal. So vertical line, perfect vertical line. So try your best. You can do the exact same way that I did. And here, what you see here is a light beam. So you see like these yellow color straight lines, those represent the light rays. A light beam means a combination of parallel light rays. Now we need to add a mirror or a lens, right? So let's use a mirror. So in the first part of the experiment, you need a plane mirror. So you go to mirrors and select segment. Then you go back to the black screen over here where your working area, and then draw a straight line. Just drag it down so that way you can draw a mirror, right? So I draw a mirror which is a plane mirror like your bathroom mirror, and I draw this line parallel to the beam producer, right? So it is a perpendicular to the incoming beam, and you see the light beams get reflected back going in the same path as its incident. Now incident angle is 90 degree and the reflected angle is 90 as well. Now in the second part of the experiment, you need to change this angle of the plane mirror. In that case, what you have to do is you go click on one corner of this plane mirror and then move it. So you can change the angle of the plane mirror. That way you can observe that the light rays can bend accordingly, right? So you can bend the light rays like this. Even here, the incident angle is same as the reflected angle. So if you draw a perpendicular line to the mirror, and if you measure the angle between that perpendicular line, which is we call the normal, and if you measure the angle from the normal to the incident beam, and again, if you measure the angle from the perpendicular plane normal to the reflected light rays, those two angles are equal to each other. Here in this simulator, there's no option of measuring those angles, but you can eyeball it, right? So the incident angle is same as the reflected angle. Okay, now we need a different mirror. So I don't need the plane mirror anymore. So what I have to do is I have to delete this segment. So I select on that one, then you can delete it. All right, now I need to get a caved or a concaved or a convex mirror. So concaved and convex mirror shapes are depend on where it's caved. So you may have a look on the lab manual and get an understanding of what is the shape of a concave mirror and a convex mirror. So anyway, so to draw that mirror on this simulator, you go to the circular arc, and then you select over here. It will put a one dot there, and I will put another dot all the way down here. I want to cover the entire beam, so I'll click there. And also you can move the cursor, changing the shape of this mirror, right? See here, that's an ideal concaved mirror. So in this case, you see the light beams get converge, right? It's collecting into one point over here. That point is called the focal point. So depending on the curve of this mirror, you can change the focal point. So here we say the focal point is somewhere on this side, right? So it is in the same side as the incident light rays are. Now, let's say I want to make this mirror into a convex mirror. This is a concave mirror. You see, like there's a caved shape, right? See, it is a caved shape. Now I want to make this convex mirror. In that case, I want to flip this shape. All right, now here it is a shape of a convex mirror. These are mirrors because the incident light rays and the reflected light rays are in the same side. Now here, this is a convex mirror and the light get diverge. So it is not collecting into one point. But there's one cool thing. Now, if you look at the extension of these light rays virtually, so I can add an extended rays here. Do you see that? So it's collecting in the back of the mirror, right? So that is a virtual focal point. So that is the focal point of the convex mirror, and it is in the back side of the mirror. So in a convex mirror, the light rays gets diverged, but they can extend back of the mirror and collect it into the focal point. So you can measure the distance from the focal point to the mirror, and that is called the focal length. All right, so we are done with using the mirrors. So we just analyzed 3 shapes of mirrors. Those are commonly used in real life. And then we need to use lenses, right? In that case, we need to remove this lens. So what I'm going to do is I'm going to delete this mirror. I get rid of the mirrors. Now I'm going to draw a lens. So lenses are made out of glass as it listed over here. In real life, the lenses can come with different materials like plastic, glass, depending on the needs, right? So let's say I want to get a ideal lens. So here I'm not going to draw the shapes like I did for the mirrors, but I like to go with ideal lenses. So it will do a really good job on the simulator. So ideal lens. Now, as you see, there are 2 types of lenses that we're going to study. One is convex lens and the other one is a concave lens. So here, when you draw a lens, so what I did was I select glasses and go to ideal lens, and I'm drawing a lens here. Honestly, I don't need the extended rays, so I need only the rays. Now here, I draw a lens, but it does not look like a lens at all, right? It is just a straight line. So that's why it's called an ideal lens. So you don't see the real shape of the lens, but you can analyze this lens by looking at the focal length. So in this one, it does have a focal length of positive 100. Here, I don't know the units, but let's say 100, right? So length can measured in different units like nanometers, millimeters, centimeters, miles, kilometers, right? So we are not going to worry about that one here. So we don't care about the units, but we're looking at whether it is a positive or negative. So here, for this lens that I draw here, it does have a positive 100. That means it is have a positive focal length, right? So when we have a positive focal length, that is a convex lens. So this is not a mirror. This is not a concave lens. It is a convex lens. So in a convex lens, light beams get converge into one point. So this is the focal point of this lens. And if you measure the distance from here to here, it should be 100. Okay, so whatever the units that we use. Then we need a, let's say I need a concave lens. So in the concave lens, it should be opposite of the convex lens. So basically in a concave lens, the parallel light beams get diverge. Now I can change this lens to a concave lens by changing the focal length to a negative value. So please observe the simulator here. So when we change the focal length to a negative value, did you notice that? So now the light rays are not really converging, it's get diverge, right? So the light rays get spreads apart. So that is diverging of the light rays. Now, if you use a Now notice the number here, it is -100, right? So that is a negative focal length that represent a concave lens. Now, if we extended the rays, you see it is collecting somewhere in front of the lens, right? So it is in the same side of the incident light rays. So we say that the concave lens have a lenses have a virtual focal point, which is a due to the divergence of the light rays. All right, so I don't need these extended rays, so I need to go back to the rays. All right, so I do have a concave lens here. Let's say I want to analyze a combination of lenses. So I need to introduce a new lens. In that case, I will move this lens a little bit towards the beam or origin, and then I'm going to introduce another lens. So I need a another ideal lens, and I'm going to draw that lens somewhere here. All right, now what type of lens did I draw here? So it is a positive 100, right? So it is positive focal length, so that is a convex lens. Now here's a combination of two lenses. One is a concave lens and the other one is a convex lens, and I was able to collect that light rays that's diverge from the first lens, right? So likewise, we can change these lenses and use it in a different combination. So let's say I want to change it to another negative value. So basically a combination of two concave lenses. See, like I can spread it further apart and extend rays, I can change the focal point into a different fashion, right? So depending on what is the application that we need, we can change the combination. So we can use a whole bunch of lenses depending on our needs, right? All right, so here, if I introduce another lens, for fun, let's insert another lens. Okay, here. So I can change this one, and I can change the location and change the focal point, right? So likewise, we can use a different combination of lenses and create another application. So in the real life, best example is correcting our nearsightedness and the farsightedness. So depending on our needs, we decide on the combination of lenses that we're going to use. So next part of the lab, where you're going to try the application for the correcting the nearsightedness and the farsightedness, we will be using a different simulator. So you go visit the second simulator that I listed on the lab manual, and it will open you to a simulator like this one. So here it is the this simulator represents the optics of the human eye. This is just a schematic sketch, but I like to see the eye anatomy, right? So if you go move the cursor to this side, you can see the anatomy of the eye. So if you are a biological person or if you are going to be a nurse, you can read these names and you can understand the parts of an eye. Anyway, so in this lab, we are mainly focusing on lenses and how it's work. So here there's a lens, and I'm looking at a normal vision eye, like having no issues. So let's say this person is looking at a faraway object with the far focus in the eye. So in this case, this is our eye lens. So can you recognize what shape of the lens is? It is a convex lens, right? So it is a convex lens which has a positive focal length. Now the object is here, the light rays, the blue color lines are representing the light rays that get collected in the back of the retina, right? So it is the retina over here. And our human brain can read this picture. So it's a nice and clear picture of a faraway object that we are seeing using our eye lens. Now let's say this person is suffering from a nearsightedness. Now, so the people who suffer from nearsighted problem, that means that person cannot see the faraway objects nicely. This person can observe near objects nicely, but not the faraway objects. So here, here's an object with far away. So I change this to far, and my object position is far. In this case, do you see that the light rays are not collecting in the retina? It's collected somewhere in front of the retina. That means this person cannot see a proper focused image. It will be a little bit blurry. So in this case, we need to correct this disorderness. So let's correct it. So you can click over here and correct the nearsightedness. Do you see that? So we apply a lens combination here. So our human eye lens is a convex lens, and in front of that we're going to use a concave lens, right? So by using that concave lens, what we did was we now see the light rays travel refracted from the external lens and then go through the eye lens, and it's travel and create a image in front on the retina, right? So in this case, this person can see a nice clear focused image. Similarly, so this person is suffering from nearsighted. So if you go for a near sight and looking at the near object, that's no problem, right? So this person is seeing a really nice view here. Now, let's say this person is suffering from farsighted. So click on the farsighted, and farsighted means this person can see only the faraway objects, right? So let's say this person is looking at a far object, so there's no problem. The image is created in the retina nicely, so this person can observe a really nice image of that faraway object. But this person is suffering from farsighted, right? So he cannot see the near object. So let's see the near object. So what happens here? So the near object is creating an image passing the retina. So that means this person cannot see a clear image. So we can correct this the farsightedness by adding another external lens. So our eye glasses, right? So here we introduce a convex lens, right? So it is a convex lens and the image pushed back to the retina, and this person should be able to see the object really nicely. Well, I hope this video will help you to understand the lab and complete it properly. So I would advise you to start it a little ahead, so you're not waiting for the last minute help. Thank you, and hopefully I'll see you somewhere on campus in the fall.